morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn one of the topic in electromagnetic waves and transmission lines as condition for minimum attenuation and distortionless transmission. Okay, so before going to derive the condition for minimum attenuation and distortionless transmission line equations and mathematical expressions, let me introduce first what actually attenuation constant and phase constants. Now, from that attenuation constant we are supposed to consider. Now, from that we will derive the expression for minimum, the condition for the minimum attenuation. So as we know that the attenuation constant is resembles with alpha, then to get the minimum attenuation, the following condition has to satisfy, right? So that condition is given by here, d alpha by dl is equal to 0. So alpha is the notation for attenuation constant and L is for length of the transmission line, and where this L is for inductance of the circuit, right? So to get the minimum attenuation, the condition which is to be satisfied is d alpha by dl is equal to 0, right? So in order to evaluate this equation, first we need to know what actually attenuation constant alpha. So that is the equation is obtained from the propagation constant gamma, which is given by alpha plus j beta, and along with the primary constants of a transmission line, the propagation constant gamma is given by root over r plus j omega L into g plus j omega C. Right? From these two equations, if we equate alpha plus j beta as gamma, which is equal to root over r plus j omega L into g plus j omega C. Right? So if we equate these two equations and by considering squaring on both sides and by considering magnitude on both sides, then we have been evaluated the equations for alpha as real term and the beta as the imaginary term, right? So depending upon this alpha and the beta, we have evaluated the lossless transmission line propagation constant and characteristic impedance of a lossless transmission line. So here first, in order to find the minimum attenuation condition, we just consider alpha and we are differentiating that equation with respect to L. So to get the minimum attenuation, we need to consider the following condition, means it must satisfy the following condition, and that condition is given by d alpha by dl is equal to 0, right? So from that alpha equal to, if alpha equal to root over 1 by 2 into rg minus omega square lc plus square root of r square plus omega square l square into g square plus omega square c square. This is the expression which we have evaluated in the previous lectures, that is the attenuation constant alpha of a transmission line from the propagation constant. So consider this as the equation where it consisting of all the primary constants of a transmission line. Those are resistance or inductance L, capacitance C, and the conductance G. Along with that, operating frequency of a transmission line, that is also there, that is omega. So it consisting of alpha equal to root over 1 by 2 into rg minus omega square lc plus root over r square plus omega square l square into g square plus omega square c square. Okay. Now apply this alpha to the condition which is to be considered for condition for minimum attenuation. So d alpha by dl is equal to, so d by dx of means d by dl of alpha equal to. So suppose if we consider here d by dl of alpha means, so if you observe in this equation where L is existing two equations, means here is the L, the first term it consisting of L, and here also the L term is exist. So in order to differentiate that equation, we have to consider the formula as d by dx of u comma v differentiation formula. And this will be given by here differentiation of u comma v means the formula is given by d of u comma v means differentiation of u comma v is obtained as u dv minus v du by v square. Right? This is the formula. So now in order to evaluate this one, first we need to consider, first we are differentiating this one, and the second one will be treated to be a constant, and second in order to evaluate the second term v du, first we have supposed to consider second term as a constant, and we are differentiating the first term, right, by v square. So here in the denominator, first consider v square term. So what is that? This is the u, and here it will be v. V square means already in place of v, we have the term inside the root. Then square means that square root gets cancelled. In the denominator, we have to left out the total thing as the. So 1 by 2 into rg minus omega square lc plus root over r square plus omega square l square into g square plus omega square c square. Okay. Now 1 by 2 into, so for root it will be 1 by 2, root x is given by d by dx of root x can be given as 1 by 2 into x power 1 by 2 minus 1 minus 1 by 2 means 1 by 2 root x. So like that, if you apply here 1 by 2, for root it is 1 by 2, and into, first if you consider this term as differentiation, means the first term is to be considered as a constant, that is g square plus omega square c square into, in this term if you differentiate, then 2 omega square L. Why? Because omega square is a constant, and if you are integrating, differentiating this one with respect to L, means differentiation of L, d by dl of L square means 2L into that thing, hence it is 2L means 2 omega square L into the total thing is g square plus omega square c square by the denominator, that is under root of r square plus omega square L square into g square plus omega square into c square. So this total thing is given by 1 by root x. So that's a 1 by 2 into this root term is given, and minus. In the second case, if you consider it as a constant, means if you are differentiating this one, first term will be a constant. Now integration, differentiation of this one thing is given by minus 2 omega square c. Why? Because already we are integrating this one, differentiating this one with respect to L term. So minus 2 omega square c by 1 by 2 into rg minus omega square lc plus root over r square plus omega square L square into g square plus omega square c square, which is equal to 0. Right? So if this, the total term is equal to 0, means the entire denominator term tends to 0, followed by this 1 by 2 also equal to 0. This 1 by 2 is also equal to 0. And if you take in between these two, this 2 and this 2 as common, then 2 is also becomes 0. Right? So now from that, see, d alpha by dl is equal to the total thing, which is equal to 0. Now if you equate, the total denominator term is equal to 0, and this 1 by 2 also equal to 0, then it becomes 2 omega square L into g square plus omega square c square by root over r square plus omega square L square into g square plus omega square c square minus 2 omega square c equal to 0. Means the total denominator term tends to 0, and we'll have the term which is there in the numerator term. So that numerator term, what it consisting of? Numerator means 2 omega square L into g square plus omega square c square by under root of r square plus omega square L square into g square plus omega square c square minus 2 omega square c equal to 0. Now if you take 2 as common, or which is equal to, means from this 2 means 2 omega square L into g square plus omega square c square by root over r square plus omega square L square into g square plus omega square c square. which is equal to 2 omega square c. So this 2 and this 2 gets cancelled. Then if you find here also omega square as common, omega square also gets cancelled, then which is equal to, means omega square L. First if you take common as 2, then 2 gets cancelled. Now omega square L into g square plus omega square c square by root over r square plus omega square L square into g square plus omega square c square equal to omega square c. Now both sides if it gets cancelled, omega square gets cancelled, then L into g square plus omega square c square by root over r square plus omega square L square into g square plus omega square c square is equal to c. Okay. Then L is equal to, see in the denominator, see this is the equation which is equal to, see L into g square plus omega square c square by denominator, means r square plus omega square L square into g square plus omega square c square is left out, which is there in the root 2. Then if you are writing the numerator term is also in the inside the root, then it becomes g square plus omega square c square whole square by r square plus omega square L square into g square plus omega square c square. Okay. So this term and this term gets cancelled, which is equal to c. Now from this we are going to write L into root over g square plus omega square c square by r square plus omega square L square equal to c. Okay. Now if we take this L into this side, then it will be in the denominator. Why? Because the L is there in the LHS part, it will be in the numerator. If you consider it in the RHS part, then it will be there in the denominator. Okay. Then L is equal to root over g square plus omega square c square by r square plus omega square L square equal to c is to be obtained. Now from this cross multiplication between these two, we can separate this one into roots as like L into root of g square plus omega square c square by root of r square plus omega square L square equal to c. Now if we cross multiply these two, then it becomes L into root of g square plus omega square c square equal to c into root of r square plus omega square L square. Okay. So after this is the equation is to be obtained. Now by considering, means in order to separate our real terms, means resistor, inductor, capacitor and conductance as separately, then by considering square on both sides. Why? Because if you observe LHS part as well as RHS part, both sides square root terms are exist. To cancel those, we just consider square on both sides. So square on both sides. Now squaring on both sides gives us this, means L square into this square and this gets cancelled. Here this square and this gets cancelled. Square will be left out, means g square plus omega square c square, which is equal to c square into r square plus omega square L square. Okay, so that will be L square into g square plus omega square c square, which is equal to c square into r square plus omega square L square. Now if you consider squaring on both sides, here without the single term is to be considered as square and the square root gets cancelled. Then the remaining term is to be written as L square into g square plus omega square c square equal to c square into r square plus omega square L square. Okay. Then by multiplying these two separately, L square g square plus omega square L square c square equal to c square r square plus omega square c square L square. See, if you observe in both sides, is there any common term? Means omega square L square c square is there, and here also omega square L square c square is a common between two. So both sides these two terms gets cancelled, hence L square g square equal to c square r square. Okay. See, L square g square equal to c square r square. Now to get cancelled, one step both sides, squaring square root on both sides. Now L square g square equal to c square r square. right? Both sides if you consider square root, then square root gets cancelled. Lg equal to Rc is to be obtained, or L by C equal to R by G. L by C equal to R by G is called distortionless condition, or the condition for the minimum attenuation. Okay. So the condition for the minimum attenuation means, which is given by here, distortionless condition, that is L by C equal to R by G. Okay. How we have been evaluated this one? First we have considered, means to cut the minimum attenuation condition, one condition must be satisfied, that is d alpha by dl equal to 0. Now in order to differentiate that one, we just consider alpha equation, which is to be expressed in terms of all the primary constants and along with the operating frequency, that is alpha equal to root over 1 by 2 into Rg minus omega square Lc plus root of R square plus omega square L square into G square plus omega square C square. Now, if you observe this one, it has considered to be root x. Root x means differentiation, means x power 1 by 2 we can consider, then 1 by 2 into x power 1 by 2 minus 1 as the differentiation 1, hence it will be 1 by 2 into 1 by root x. Okay, then from that the numerator term is to be considered as according to differentiation of UV rule, then u dv minus v du by v square, like that. Then it will be obtained as d alpha by dl is equal to 0. From that we have been evaluated the condition as L by C equal to R by G, and it is also called as distortionless condition, or minimum condition, the condition for minimum attenuation. Okay. Then attenuation, that's what we have considered the constant as alpha. Why? Because alpha is the notation for the attenuation constant. Next, distortionless transmission line. So to evaluate this distortionless transmission line, we need to consider propagation constant gamma and the characteristic impedance Z0. Okay. Now, a line in which there is no phase or frequency distortion and also it is correctly terminated is known as distortionless transmission line, noiseless transmission line, right? So what do you mean by distortionless transmission? How we can define? Means a transmission line in which there is no phase or frequency distortion and it is also properly terminated, then it is said to be distortionless transmission line. So to derive the condition for that distortionless line, first we have to consider gamma. That gamma in general is expressed in terms of all the primary constants as root over R plus j omega L into G plus j omega C, right? Now in this we can separate real and imaginary terms. Means by squaring on both sides, gamma square will leads us, which is equal to gamma square equal to root over R plus j omega L into G plus j omega C whole square. Okay, so square root gets cancelled, then it will become R plus j omega L into G plus j omega C by multiplying these two. So if you multiply these two, then what you are going to get? R plus j omega L into G plus j omega C equal to Rg plus j omega Rc plus j omega Lg minus j into j becomes j square omega square Lc. Then real and imaginary means Rg minus omega square Lc plus, if you take j omega as common, Rc plus Lg. Okay. So see here, gamma square equal to Rg minus omega square Lc as real and imaginary as j omega into Rc plus Lg. Okay. So here C is not there. Then we know that for a minimum attenuation, what is that condition? See, L by C are equal to R by G, or Lg equal to Rc, right? So if you substitute either of the two, means Rc by Lg or Lg by Rc, then it is easy to simplify. For that, we know that for minimum attenuation condition, L is equal to Rc by G or simply Lg equal to Rc. Okay. Now in place of Rg by means in place of Lg by if we substitute Rc, then it becomes, see, if you substitute Rc by Lg, then it becomes Rg minus omega square Lc equal to, plus j omega into Rc plus Rc means 2j omega Rc, right? So gamma square equal to Rg minus omega square Lc plus j2 omega Rc. Okay, by substituting in place of Rc by Lg or Lg by Rc, Rc plus Rc becomes 2Rc. Okay, then but Rc equal to Lg equal to root over Rc into Lg. Rc equal to Lg equal to root over Rc into Lg. Means if you multiply those all and all, means in place of these are all, we substitute Lg by Rc or those things, then Rc equal to Lg equal to root over Rc into Lg. Now in place of this thing Rc by, if we substitute Rc into Lg, then gamma square equal to Rg minus omega square Lc plus 2j omega root over Rc into Lg. Okay, then see gamma square equal to means gamma square equal to root Rg plus j omega into root Lc. See, Rg minus omega square Lc plus j2 omega Rc. Then in place, if we substitute real and imaginary terms, then we can get here, see, gamma square equal to root Rg plus j omega into root Lc. Right? See, root Rg in this one thing, gamma equal to root Rg, and this becomes, means, if we substitute Rc by this thing, Rc by Lg, means 2 gets cancelled, 2j omega is left out. Now from this we can get gamma square equal to root Rg plus j omega into root Lc. But according to gamma, alpha plus j beta, right? So gamma equal to alpha plus j beta. So by comparing both sides real and imaginary terms, alpha is nothing but root Rg and beta is nothing but omega root over Lc. Okay. Then alpha equal to root Rg and beta equal to omega root over Lc. Right? For a distortionless transmission line, attenuation constant alpha is nothing but root Rg and the phase constant beta is given by omega root over Lc. Omega root over Lc. Right? So alpha does not vary with frequency. Why? Because it won't consisting of any frequency components. Hence, alpha does not vary with frequency, which eliminates the frequency distortion. Okay, and as we know that velocity V, phase velocity or wave velocity can be defined as Vp equal to omega by beta, which is equal to omega by root over Lc. Why? Because Vp equal to omega by beta, then omega by, if we substitute beta, means omega root over Lc for the distortionless transmission, then this omega gets cancelled. Vp equal to omega by beta equal to 1 by root over Lc. Right? So for the condition Rc equal to Lg, the velocity becomes independent of the frequency, and this eliminates the phase distortion. Okay, for the condition Rc equal to Lg, the velocity of the wave becomes independent of the frequency. By this, we can eliminate phase distortion. Okay, now from this attenuation constant alpha and the phase constant beta, how we can eliminate frequency distortion and the phase distortions means, see, if you observe for a distortionless transmission line, alpha is to be obtained as root Rg and beta is omega root over Lc, right? Depending upon alpha, we can eliminate frequency distortion. How? Means alpha does not vary with any frequency components, hence it can eliminate frequency distortion. And if we observe according to the distortionless condition, we have observed Rc equal to Lg or L by C equal to R by G, then according to that, the velocity becomes independent of the frequency components, and this will eliminate the phase distortion. Okay, then All the distortions are eliminated for a condition that is RC equal to LG or nothing but L by C equal to R by G is called the minimum attenuation condition or distortionless transmission line condition is given by L by C equal to R by G. According to this propagation constant gamma of a distortionless transmission line, then along with this propagation constant, we are also able to write the equation for characteristic impedance Z0. And here Z0 can be given by Z0 is equal to root over R plus j omega L by G plus j omega C. For a distortionless condition, we know that since it is L by C equal to R by G. L by C equal to R by G. Right? So, if we substitute or from this equation, characteristic equation, Z0 is equal to root over R plus j omega L by G plus j omega C. Now, if you find from the numerator part, if you consider R as the common, then 1 plus j omega into L by R by, if you take G as common here, 1 plus j omega into C by G root over. Okay. See here, C by G or L by R. So, suppose if you cross multiply these two, then from this L by C equal to R by G, if you write L by R equal to C by G also, means in place of L by R, if you substitute C by G, or in place of C by G, if you substitute L by R, then it is easy to simplify the equation, right? So, which is equal to, means Z0 equal to root over R into 1 plus j omega. We substitute L by R by what? C by G. Right? By then G into 1 plus j omega into C by G is nothing but or C by G. Why? Because we have considered there in the numerator as in place of L by R by C by G. Hence 1 plus j omega into C by G, and in the denominator 1 plus j omega into C by G is exist. So numerator term and denominator term gets cancelled. Hence Z0 is equal to root of R by G is to be obtained, and R by G is nothing but, according to this relation, distortionless transmission line, R by G equal to L by C. Hence root of L by C. See here, Z0 is equal to root of R by G, which is equal to root of L by C. So this is the condition for distortionless transmission line characteristic impedance. See, alpha does not depend on frequency, whereas beta is a linear function of frequency, and characteristic impedance Z0 is always a real term, that is root of L by C or root of R by G. And this is to be obtained for the minimum condition of attenuation, or the condition to get to evaluate minimum attenuation as L by C equal to R by G, right? So characteristic impedance Z0 is equal to root over R by G equal to root of L by C. So in this what we have learned is a distortionless transmission line. To write the mathematical equations for this distortionless transmission line, first we have to consider how the frequency and the phase distortions are to be eliminated, how effectively the line is to be terminated properly. Depending upon that, the line is said to be distortionless line. Means a line in which there is no phase or frequency distortion and it is perfectly terminated, then it is said to be distortionless transmission line. To get the condition, we first consider distortionless transmission line. First condition as L is equal to RC by G or LG equal to CR, and this is from L by C equal to R by G. Now if you replace L by C by R by G or this thing, then gamma square equal to gamma, first we have to consider root over R plus j omega L into G plus j omega C, and if you evaluate that one, r plus j omega L into g plus j omega C by squaring on both sides. Now by comparing real and imaginary terms, then alpha becomes root rg and beta becomes omega root Lc. Right? So with that attenuation constant alpha, the frequency distortion is to be eliminated with the formula Vp equal to 1 by root Lc, which is equal to 1 by root Lc. And similarly, for the condition Rc equal to Lg, the wave velocity becomes independent of the frequency. From this, phase distortion is to be eliminated. Now, all the distortions are eliminated for the condition that is Rc equal to L by G, or simply L by C equal to R by G. Okay. Then, from the characteristic equation, all the primary constants are evaluated in terms of or existed in terms of along with the operating frequency. The characteristic impedance of a transmission line is given by root over r plus j omega L by g plus j omega C. Now in this, if you consider the term means minimum condition as L by C equal to R by G. Now if you take in the numerator R as common, 1 plus j omega into L by R, and if you take denominator G as common, 1 plus j omega into C by G is left out. Now according to the distortionless condition, if we substitute L by C by R by G, then it becomes here numerator term and the denominator terms are getting same. Then by gets cancelled, then it becomes Z not equal to root over R by G is left out. Now from this root of R by G, we substitute L by C. According to the distortionless condition, we substitute R by G by L by C, then Z not equal to root of R by G equal to root of L by C. And where alpha does not depends upon the frequency and beta is the linear function of the frequency. According to the distortionless transmission line conditions, alpha, beta and gamma along with that characteristic impedance Z naught are to be evaluated. Now, we can tabulate all the characteristics of a transmission line, right? So in general, how the propagation constant and the characteristic impedance are to be existed, and in the lossless condition and in distortionless condition, how those two are to be evaluated, right? So already these are all evaluated in the previous lectures. Now we are tabulating all in a particular table. So first case. So there are 3 columns here. In the first column, we have considered case means general type or else lossless type or else distortionless type. And in the second column, we have been considered propagation constant and the notation is given by gamma. And in the third, we have considered the characteristic impedance as Z naught. Right? So for a propagation constant gamma, we should be expressed in terms of all the primary constants along with the operating frequency of a transmission line. Then general case it is given by root over R plus j omega L into G plus j omega C, where resistance R, inductance L, conductance G and the capacitance C or 4 are called primary constants of a transmission line and omega beta angular frequency of a transmission line. Right? And in general, it is given by omega equal to 2 pi f. Angular with an angle, it is multiplied with frequency, hence the name has given angular frequency, right? So the operating frequency or angular frequency is omega here. And in terms of all the primary constants of a transmission line and with the operating frequency presence, then characteristic impedance Z naught is given by. So Z is the notation for impedance and where Z naught is resembles characteristic impedance. So it includes all the primary constants along with the operating frequency and it is given by Z naught equal to, and here gamma equal to. Z naught equal to root over R plus j omega L by G plus j omega C. Now in this case, lossless condition. Lossless condition case means how we are going to get lossless condition means there now to provide all the primary out of all the primary constants R, L, G, C, where L and C are said to be storing elements, whereas resistance R and G conductance are said to be dissipating elements, right? So power dissipation is to be considered according to resistance R and the conductance G. Hence, we must equate R equal to 0 and G equal to 0 in that particular case. So consider general case as gamma root over R plus j omega L into G plus j omega C. In that, you just substitute R by 0, G by 0, then it becomes C. Root over j omega L into root over j omega C. See, gamma equal to j omega L into j omega C is left out. Then this becomes j omega root LC. And we know that alpha plus j beta is given by gamma. Now from this, alpha equal to 0 and beta equal to omega root over LC. Okay. So from this, alpha equal to 0, that's why 0, and beta is nothing but omega root over LC. Okay. So for a lossless transmission line, the propagation constant constitute only phase, means imaginary. That is, attenuation constant alpha equal to 0 means there is no reduction in the amplitude, means there is no loss in the signal, hence it is said to be lossless transmission line. It consisting of only imaginary part, and that is represented with phase constant as beta, that is beta equal to omega root over LC. Okay, then, and the characteristic impedance. Now, in general, characteristic impedance is given by root over R plus j omega L by G plus j omega C. Now, in that, you just substitute again R by 0 and G by 0. Then it becomes root over j omega L by j omega C. Then j omega gets cancelled. Root of L by C is to be obtained for the lossless transmission line characteristic impedance. Okay, root of L by C. Now, second condition is given by here, means in general and the lossless conditions we have seen just now. Then after that, distortionless line. So to find this distortionless line, we need to know first the condition for minimum distortion or a distortionless transmission line, and it is given by L by C equal to R by G. Okay, use this as the condition to simplify the distortionless transmission line, propagation constant and characteristic impedance. So that is given by, for the propagation constant, gamma equal to alpha plus j beta. Now if you evaluate that one, root over means gamma in general equation is given by root over R plus j omega L into G plus j omega C, and if you substitute in place of that R and G by RG by omega C, sorry, L G by RC or else RC by LG, then it becomes alpha equal to root RG and beta equal to omega root LC. Okay, so this is the way we have evaluated attenuation constant alpha and the phase constant beta, which constitute propagation constant of a distortionless line, by considering L by C equal to R by G is the minimum condition for the distortionless line. And after that, characteristic impedance also to be evaluated. So that how we have been evaluated means Z is equal to, if you consider root of R plus j omega L by G plus j omega C. In that, if you consider, in the previous case already we have evaluated that one. So in between this one, in the numerator, if you take R as common, 1 plus j omega into L by R, and in the denominator, if you take G as common, 1 plus j omega into this C by G. So if according to this condition, distortionless condition, then L by R equal to C by G, then 1 plus j omega into C by G is the common between numerator and the denominator. So both gets cancelled, root of R by G is left out. Then according to that condition, L by C equal to R by G, then which is equal to L by C also. Or in other words, how we are going to evaluate this one? Means Z naught is equal to root of R plus, if we take, means R by L plus j omega. Means if you take in the numerator L as common, then R by L plus j omega by, in the denominator, if you take again C as common, C, then G by C plus j omega. Right? So if you substitute R by L means L by C equal to R by G is the fundamental one. From that, if you write R by L is equal to R by this L is equal to G by C. Okay. So in place of R by L by, if you substitute G by C or G by C by R by L, then these two becomes same. Means first if you substitute, I am substituting here L by R by L by G by C. Then G by C plus j omega into L by here G by C plus j omega into C is left out. See, if you observe in the numerator and denominator, these two are same, hence 2 gets cancelled. Then root of L by C is to be obtained. So this is the case. We have got root R by G. Now from this relation L by C equal to R by G, we can equate root of L by C. Now from this relation we can equate root of R by G. Right? So from this, in the tabulated values, the characteristic impedance of a distortionless transmission line is given by root of L by C. Z0 is equal to root of L by C equal to root of R by G. Okay. So what we have learnt is in the this particular lecture, first we have been evaluated the attenuation, the minimum condition for attenuation. So now to evaluate that, we have considered the attenuation constant alpha, and from that we have now to derive the equation for that, it must satisfy for the simple condition, that is d alpha by dl is equal to 0. To derive to satisfy that condition, we have considered the attenuation constant alpha equation, which includes all the primary constants along with the operating frequency. Then it looks like a differentiation of root x form. Then we have been evaluated that complete equation. Then from that we have got root of L by C equal to R by G as the condition. Then we have learnt distortionless transmission line. For that, attenuation constant alpha, phase constant beta, and the propagation constant gamma is to be evaluated. Along with that, characteristic impedance Z0 may also be evaluated. Now, in general, propagation constant gamma and the characteristic impedance Z0 consisting of all the primary constants along with the operating frequency or angular frequency. Then we have been tabulated the 3 different cases as here, general case and lossless case and distortionless transmission line case. We have compared propagation constant gamma and the characteristic impedance Z0. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.